Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we are continuing with our examination of substitution and elimination reaction mechanisms. In this lecture, we're going to be looking at the Elimination Bimolecular or E2 reaction mechanism. Now, in the E2 reaction mechanism, it is similar to the SN2 in that we have a one-step concerted process. That is, base attack and product formation all happens in one smooth step. I'm going to use a powerful base, such as hydroxide minus, and I'm going to react it with the following alkyl halide. And I'm going to show an H here. And I'm going to draw a bromide. So propylbromide is attacked by hydroxide. What we have here is the base goes for the proton. The two electrons from the carbon-hydrogen bond create my bond, my pi bond. And it might be worth drawing that. So why not? Put a bond here. And let's put a bond to bromine. So you can actually see where so we make a pi bond here, and then the electrons from the carbon-bromine bond go to a bromine. Now we could draw a transition state for this that shows it quite well. The hydroxide two lone pairs here, attacks the H, and I'm using blue for bond breaking. So we'll have a CH here, connected to CH, of course, was a CH3. We have a CH2, and again, bond breaking, bond to bromine. So I'm going to make this bracket a little taller. This is our transition state. And I'm going to use red for bond forming. Now the hydroxide was originally negative, so there is a delta minus here. And the hydroxide is losing its negative charge, and the negative charge is transferring to the bromine, so it gets a delta minus. I can write bond breaking. And obviously it's the blue ones. And again use red to write bond forming. And so we have a bond forming between the hydroxide and the hydrogen, and the pi bond is forming. Consequence of this transition state is the formation of H2O and the molecule propene. Now in the E2 reaction mechanism, we can actually draw a different perspective of the transition state. What would I see if I actually put my eyeball, say, here? So I was looking down that carbon-carbon bond in which the pi bond is forming. I could draw a Newmann projection representing this transition state. The carbon in front has two hydrogens, and normally you draw the two hydrogens sharply angled, representing sp cubed, but they're beginning to flatten out. I'll show you what I mean. Normally I would draw them quite steep like this in a Newmann projection. But because it's going flat, I'm going to draw them a little straighter. Okay? So you'll notice that from where they normally were, I move these two groups down as I begin to flatten them out. This is part of the rehybridization. Once you form the double bond, these two carbons are changing the hybridization from sp cubed to sp squared. So in the transition state, that is partially happening. So when I actually draw this, let's repair my circle. As much as I can. I will draw the two hydrogens. That's not very good. In flatter positions. Okay, the two in behind are starting to tilt up, the CH3, and so they're flattened out as well, CH3 and the H. Now in behind we have a bond breaking to the H. And in front we have a bond breaking to bromine. Now I can show the red bond forming at least to the hydroxide, so we can put that over here. But I can't show the other bond forming, so let's write bond forming here. Because the other bond forming is along the carbon-carbon bond that we're looking at, and that represents the pi bond. So if you like, there's a bond forming here. There. And there is a bond forming right here. But I can't really show that because that's the axis we're looking down. And so we have a bond breaking. So you also can draw transition states as Newmann projections. You don't just have to draw a regular structural formula. And so there's an OH here. And of course, as before, it's delta minus. The bromine's delta minus. So that, if you like, is my Newmann projection of the same transition state. Now what the Newmann shows is the orientation of the two groups that are leaving much more clearly, if you like. and what's happening to these substituents as the pi bond forms, how they're flattening out, if you like. Now that brings us to the key features of the reaction mechanism, which we can begin to talk about. So let's try squeezing a lot onto this slide. Key features. Okay. Well, the first key feature obviously is very similar to the SN2 reaction, and that is we have a bimolecular reaction. In this regard, the two reactions are similar. They are single steps. And both reagents are involved in the formation of the transition state of the slow step. Since there's only one step, there's only one slow step. Both reagents are involved. Hence, changing the concentration of either reagent will increase rate. It's bimolecular because the rate of reaction depends on two of the reagents. Two of the reagents are involved in determining the formation of the transition state of the rate determining step. Bimolecular. And we've discussed this, and I refer you back to the scribblecast that dealt with the SN2. Another very important aspect of the E2 reaction mechanism is antiperiplanar elimination. Antiperiplanar. Antiperiplanar elimination. What is that? Well, the departing hydrogen and leaving alkyl halide group, these two departing groups leave in an anti-orientation when you look at the Newmann projection. That is, one is leaving down and one is leaving up and away. The groups are anti to each other because this allows the 2p orbitals that are forming as they leave, when these carbons rehybridize, it allows them to be side to side. So if I draw this again, as the bromine and hydrogen leave, the 2p's that are forming are of proper orientation to allow side-to-side bonding. You see, when these 2p's are not overlapping, if, say, one was diagonal, so that they couldn't overlap 90 degrees to each other, this would be a much higher energy state. Too high energy for the hydroxide to cause the hydrogen to leave. So if you were in this orientation, when the base came in and hit the hydrogen, there'd be no reaction. The base would bounce off. Because if they left and began to rehybridize, the 2p orbitals would not be overlapping. This would result in a higher energy. The transition state in this case would be too high energy to allow reaction. Only when, as the H leaves and the bond is breaking, and the bromine is leaving, only when the two groups are anti and rehybridization to sp squared begins to happen, that is, the 2p's begin to form from the sp cubes, only then, when they're anti, do the orbitals align properly for side-to-side overlap. And these overlapping 2p's lower the energy of the transition state, that is, as they're forming. So antiperiplanar elimination allows a lower energy to the transition state, allowing the formation of the pi bond. That is, the alignment of the groups is correct to allow for the formation of the pi bond. Okay. Now I encourage you to make a model and look at the Newmann and get the group's anti. If you actually make a model and look down the bond, you can imagine, and then maybe make a model that shows the pi cloud where the H and B are located. You'll notice that this alignment is indeed possible when the H and Br leave anti to one another. And anti just means opposite. The Br is leaving in that direction, and the H is leaving upwards. Okay. Let's continue with the key features. Well, obviously, we're going to hold off on talking about this one for the moment. The reaction is stereospecific. In the E1, we said it wasn't stereospecific, so this begs some explanation so that we might define what stereospecific means and then examine why this would be stereospecific. The key feature of stereospecificity is a direct result of the antiperiplanar requirement of the elimination. And we'll show that in a little while. Key feature number 4, we have a one-step concerted process. This goes right back to the SN2. One-step concerted process, just like the SN2. Everything happens in one step. One-step concerted process. Point 5, there's a kinetic isotope effect. We could talk about this one. There is a kinetic isotope effect. What's that? Well, actually, it would be useful if I jumped ahead a couple key features and come back to this. Number 6, because it's a one-step concerted process, there's no isolable intermediates. No isolable intermediates. We have a transition state. We go through the transition state. We get products. There's nothing like in the E1. Number 7. Tertiary is faster than secondary. It's faster than primary. Which of course is faster than methyl. Methyl cannot form alkenes. So for this mechanism, methyl is not important. So methyl actually doesn't happen. Now we have to explain this trend, but let's assume that trend is true and go back to kinetic isotope effect. We have a problem here. A problem that is different than what occurred in the SN2 and the SN1 reaction mechanisms. Remember in the SN2 and SN1, we could distinguish them. The SN2 methyls were faster than primaries. In the SN1, tertiaries were faster. So you could measure rates on a tertiary system or a secondary system, and you could use rate of reaction to help distinguish between the reactions. With chirality, you got inversion in the SN2 and racemization in the SN1. So you could use chirality to help distinguish between these. But how on earth do you distinguish between the E1 and E2 reaction mechanism? If the relative rates are both tertiaries faster than secondaries faster than primary, how can we distinguish between them? Well, one of the ways is to carry out a isotopic labeling. What do you mean? Well, you could measure the rate of the reaction for this formation of propane from propylbromide. Then you could repeat the reaction, but this time, instead of using a hydrogen, removing this hydrogen, replace the hydrogen with a deuterium. Remember, deuterium is a hydrogen that has a neutron. And because it has a neutron, it is twice the mass of a hydrogen atom. Now, because of this, carbon-deuterium bonds are stronger. Okay? It is harder to remove a deuterium atom, which has twice the mass than a hydrogen atom. That means at a fixed temperature, the number of hydroxides coming in with enough kinetic energy to cause a reaction when the molecule is antiperiplanar will be less for deuterium than hydrogen. Since the number of molecules is less, the rate of product formation will be reduced. In fact, this rate in the E2 reaction mechanism is reduced by a factor of 2. Now, if you look back at the E1 reaction mechanism, you will find that the rate-determining step is carbocation formation, and that pulling off a hydrogen has nothing to do with forming carbocation. If you look at step 1 in the E1, you have an alkyl halide, you pull off the bromine, you get carbocation. There's no abstraction of hydrogen there. So changing hydrogens to deuterium does not affect step 1 at all. And step 1 is your slow step in the E1 mechanism. So in the E1 mechanism, there's no kinetic isotope effect. In the E2 mechanism, because deuterium is heavier and harder to move, and part of the overall rate, the overall activity of the step that forms the transition state, then pulling off deuterium, because it's harder, takes longer, and the rate slows down. In fact, it slows down by roughly a factor of 7 times. So all I have to do to distinguish between the E1 and E2 mechanism in alkene formation is time the rate of reaction for the hydrogenated alkyl halide, and then repeat the reaction with the identical alkyl halide where there are deuteriums in place in hydrogen, the deuterated analog. If I utilize the deuterated analog and I see a slowdown in rate, I know I'm going E2 because it shows a kinetic isotope effect. However, if I don't see any change in rate, I know hydrogen abstraction is not part of the rate determining step, and the only case that occurs for is the E1 reaction mechanism. And ergo, if there is no rate change with the deuterium analog, I must be going E1. So a kinetic isotope effect can be very useful in determining or distinguishing between the E1 and E2 mechanisms. Key feature number 6. No isolable intermediates. Well, that goes in concert with one-step concerted process. A single process, one transition state. There's no intermediate formed. Okay, what about the relative rate? Well, the relative rate, tertiary faster than secondary, faster than primary. What can cause that? Well, it turns out that this rate parallels the stability, let's go back to blue. Of the alkene. What do I mean? Stability of the alkene. Well, if we look at alkenes and the number of substituents, it turns out that those alkenes, those carbon-carbon double bonds that have more alkyl substituents, so R here is going to symbolize any alkyl group, methyl, ethyl, some carbon-bearing group. When you have 4 substituents, your alkene, according to energies determined by heats of hydrogenation, are more stable than less substituted alkenes. those that replace the alkyl groups with hydrogen. So as I start replacing these R groups with hydrogens, I become less and less stable as an alkene. Now I'm not going to explain this. We will look at this more closely when we actually look at the heats of hydrogenation when we cover alkenes. These two both have two hydrogens, so I'm going to rate them as similar for the purposes of this comparison. And they are greater than the alkene, which has 3 hydrogens, which of course is greater than the alkene, which has 4 hydrogens. Well, how does this help with our determination of relative rate? Because remember, in that key feature number 7, we said tertiary is faster than secondary. What has this got to do with alkene stability? Well, let's look at a tertiary alkyl halide, like tert-butyl bromide. If I was to pull off a bromine from tert-butyl bromide to form an alkene, and a base came in and pulled off one of these hydrogens to make a double bond, I would get an alkene that would look something like this. So tert-butyl bromide is generating an alkene of this type. So I'm going to mark this guy with the symbol tertiary to indicate tertiary alkyl halide would form this kind of alkene. Now let's look at a secondary alkyl halide. Okay, so how about, oh, I don't know. Isopropyl bromide, let's pull Br off, take off a neighboring H, and I would get something like this. There we go. That alkene is very similar to this guy. So secondary alkyl halides produce, by definition, less substituted alkenes than tertiary alkyl halides. Interesting. All right. So this trend, the tertiary alkyl halides produce more substituted double bonds, which are more stable. But why would the stability of the double bond have anything to do with the rate of reaction? Why would tertiary be fast? After all, the rate is controlled by the transition state. Well, what you can do is pause this video and just move back a few frames and scroll the cursor back to the point where you can see the transition state. And look at the bond that's forming. One of the bonds that is forming is the pi bond. Now, anything that will stabilize a pi bond will favor its formation in the transition state, because the bond is forming in the transition state. And it's forming in the transition state of the rate determining step, the slow step. In this case, there's only one step. So because the pi bond is forming in this rate determining step, anything that stabilizes, that lowers the energy of the transition state. Anything that stabilizes that pi bond formation will lower the energy of the transition state, making it more favorable. And that speeds up the reaction. So in actual fact, it is the transition state's alkene character that's being stabilized and reflected by the stability of the alkene. Okay. What is the next key feature? Well, the next one, number 8, is no rearrangement. Again, this is like the SN2. Since we don't have an intermediate carbocation, we don't see the 1,2 shifts we have occur in the E1 and SN1 reaction mechanisms. Key feature number 9, or let's not call it a key feature, let's call it a favored by statement. Overall, the reaction is favored by A, stronger bases. Notice I say bases because I'm concerned with base attack. In elimination, I'm attacking hydrogen, not carbon. When you attack H+, you are acting like a base. Stronger bases. B. Overall, stronger bases, higher reaction temperatures. And C. There is little or no solvent effect. So typically, because the E1's favored bipolar product, we do use aprotic solvents often to help with the E2. That is, the aprotics may not cause a huge increase in the E2, but rather it will disfavor the E1 from occurring. Higher temperature is typical of the elimination reaction mechanism, and stronger bases come in more quickly, giving less time for ionization. So we do use, one could say you use aprotic solvents just in order to disfavor the E1 mechanism. Now what's interesting about the two mechanisms, E1 and E2, turns out E2 is the important one for alkyl halides. E2 is the preferred mechanism followed by alkyl halides. Alkyl halides almost never go E1, and if I want to show an alkyl halide reacting E1, I pretty much have to say E1 under the reaction arrow to just tell you to use it. Because typically alkyl halides react by the E2 mechanism. And we'll be learning more about why when we see examples of molecules that prefer E1. We'll be able to contrast them. Okay, so one more thing to look at, stereospecific. But before we do, I do want to do one more thing if I can. I want to go back to my reaction trend. Key feature number 7, tertiary is faster than secondary, which is faster than primary. And I want to ask the question, why? Why does this apply in this case? Why do we have tertiary versus secondary versus primary, whereas in the SN2, if you remember the SN2 reaction mechanism, it was primary and methyl. We won't include methyl because it's not important for elimination, but primary is faster than secondary. Remember, for the SN2, primary is faster than secondary because of the backside attack, the need to get at this gray carbon here. Very difficult to do. In a more obscured tertiary case, in case you can't see it, this is tertiary, this is secondary. This is this is methyl. This is primary. We attributed it to the junk in the trunk, the steric effect that blocks or obscures the carbon from attack by the incoming nucleophile. What's interesting, though, is in the E2 case, we're not attacking the gray carbon, are we? We're not attacking there. We're actually going for a hydrogen that sticks up and away. We might be going for that hydrogen. A hydrogen that sticks off a neighboring carbon. And because of that, the hydrogens are more accessible. So whereas hydroxide, okay, let's use a different color. Hydroxide may have difficulty when it acts as a nucleophile, getting past all the junk in the trunk. In the methyl case, it's really easy, but in the tertiary case, it's almost impossible. So I'm using the red to symbolize hydroxide acting as a nucleophile. When hydroxide acts as a base, it doesn't have to go for the carbon. It could go for one of the protons sticking off in space, and they're more available. They're less, shall we say, hindered by other substituents. They're less sterically blocked. They're more available. And so what caused the primary to be faster than the secondary, and faster than the tertiary, the junk in the trunk, is not affecting rate in the E2. So something has to affect rate. And what that turns out to be is the stability of the alkene and the number of substituents. The number of substituents around the double bond. So I thought I'd spend a little time just talking about and contrasting the E2 with the SN2 with regards to rate. They are very different. What controls rate in the E2 is alkene stability. What controls the rate in SN2 was the backside attack. Which is subjected to steric effects of the substituents. The steric influence, if you like, of the R groups. Where R in this case can be hydrogen or alkyl. Okay, so SN2 and E2 have very different factors controlling the rate. All right, I hope that helps clear that question up. What I want to do is come back to key feature number 3, stereospecific reaction. Having trouble drawing an E. Stereospecific reaction. Okay, let's take a close look at this. What is a stereospecific reaction? It's a reaction in which different reactant stereoisomers. Okay, so it's a reaction where different reagents that are stereoisomers. So different stereoisomeric or stereoisomer reagents yield products that are specific stereoisomers. Let's look at an example. Suppose I have the following pure enantiomer. Over here is a phenyl. And coming out at you is a CH3. It is attached to a carbon that has going into the board an H. Oops, sorry. No, we're going to make that my phenyl. And then an H. And a Br. I've drawn a staggered conformer in which the H here and the Br are anti. They've rotated to the anti position. Okay. If I actually take the time to draw the Newmann projection of that, what I would see, this is not the transition state, this is before the transition state. So I put my eyeball here and I look down. I would see off of my left hand side would be an H. Off of my right would be my phenyl. And then coming down I would have a Br. In the carbon behind, on the right, I have a phenyl. I have the CH3 here. And I have, coming up, the H. See if I can fix that a bit. Don't know if that fixed it. Okay. Now, because these aromatic rings are going to be shrunk in size, they may be hard to see. Putting dots for the carbons, so it might be a little more visible that it is a six-membered benzene ring, just in case they don't stand out very well once they're reduced for the iPod and PSP. Okay, there we go. There we go. Now, the H and Br are anti. If I rotate about the sigma bond, the Br and the H, to any other position, elimination does not occur. The Br must be going down when the H is pulled off up. They must be anti. This anti-result means that when the double bond forms here, when the double bond actually forms here, the two phenols are on the same side. When the C double bond C forms, my phenyl and my other phenyl are all going into the board. They're on the same side. And here we have a methyl, and here we have an H. It looks like we produced the cis product. Looks like we've produced the cis product on cis alkene. Let's check out the chirality of the starting material. If I do this carbon and prioritize, bromine is highest priority. I then have a carbon and a carbon on the aromatic ring. This carbon has a carbon. Aromatic ring has a carbon. This carbon has another carbon. Aromatic ring has another carbon for its double bond. Carbon has an H. Well, there's a third carbon on the aromatic ring from the point of attachment, and so the aromatic ring becomes higher priority. And so bromine's number 1, aromatic ring's number 2, this side group becomes number 3. And if you project the H to the rear, right now it's coming out at you, so it's backwards. If you flip it around and project it to the rear using a model, you'll find if you draw a curve 1, 2, 3, then it'll be to the right. And you must project the lowest priority group to the rear. This carbon becomes R. Likewise, if you prioritize, we have carbons. This carbon has a bromine, so he's number 1. So now we're doing this carbon. That carbon has bromine is number 1. Carbon with the methyl, with the methyl carbon is going to be number 3. The phenyl is going to be number 2. And again, if we project this to the rear, the H, the low priority group to the rear, using a model, 1 to 2 to 3 will turn out to be right, and this is also R. The RR enantiomer of this molecule yielded the cis or the Z enantiomer. Why is it Z? Carbon, high priority carbon, the aromatic ring. This carbon, the carbon off the double bond, both have carbons. This carbon has H's, this has other carbons, so he's 1. Carbon's higher atomic number than H, so he's 1. Both number 1s are on the same side, so it's Z. Notice if let's change that H. If I replace this H with a fluorine, this would have been a fluorine. That would have given me a fluorine here. If that was fluorine, that would have been higher atomic number than carbon. He would have been 1. This phenyl would still be higher than CH3. The 1s would have been on opposite sides. If you had used fluorine, you wouldn't have gotten Z, you would have gotten E. So we can't say the RR always yields Z. That's not possible. It depends on the substituents and how you prioritize. But what we can say is the RR enantiomer produced a single stereoisomer, which in this case was pure Z. What if I replaced the RR, I switched it, and I made, say, the SS, rather than drawing the aromatic ring, not that my drawings are very good anyways, a phenyl group is C6H5, so I'm going to write C6H5 here. And so I'm switching on both chiral centers to groups that generates the other enantiomer. I'm still making it anti. Now the aromatic rings are on the wedges. Well, if I do my elimination on that, and I draw my alkene, well, both phenols are on the wedges now when it forms. They're both located on the wedges, and so when the Br and H, the dashes get the H and CH3. So it's still Z. This is the SS isomer, because I've changed both chiral centers. So RR gives me the Z isomer. SS gives me the Z isomer. They're stereospecific. Is there any chance in this case of getting the E isomer? Well, if I changed only one chiral center, say I did RS or SR, that would yield the trans isomer. You should attempt to do that. See what you come up with. Take the trans isomer. In fact, let's do it together. Why don't we do that? Okay? So let's try the RS, and let's make it a little larger this time. All right? And so we'll leave this one the way it was. I'm going to use C6H5 for my phenyl aromatics. And wedge for CH3. I have my H. And, well, there you have, Patches is taking off for the door again. You have, this time we're going to switch this chiral center. And so we're going to have the H on the wedge here, on the dashes, on the wedge the C6H5. And BR, we've drawn it anti. If we pull the H and BR off, you see now the C6H5 is going to form on the same side coming out at you as the CH3. When it leaves, you're going to get the CH3 on the same side as the C6H5. The other C6H5 that has the dashes is going to be on the same side as the H. When I prioritize, C6H5 is higher priority than H, carbon's higher, and this, if I follow the carbons, C6H5 is higher priority than CH3. My two high priority groups end up on opposite sides, so this is E. If you check the chirality, this center is R, that one's S. RS gives E, gives a different stereoisomer than the SS and RR case. Specific enantiomers are producing specific stereoisomers in the products. This is directly a result from the anti-elimination. There's absolutely no way you can eliminate alternatively. Now beware, you may find questions where it's not drawn anti and you actually have to rotate the groups. For example, you might get a question where the first chiral center is drawn appropriately, but the second chiral center has perhaps this. Effectively, what this is simply showing is a simple rotation. And you might be tempted to say, well, no reaction can take place because the bromine isn't anti. But remember, conformational change can occur at room temperature. Rotation is possible. This bromine can swing down. The H would swing up to the dash position, and C6H5 would swing out to where the bromine is. In fact, this stereoisomer and that one are the same thing. The only difference is a conformational, rotational change. In other words, this guy would also yield E. However, elimination would not occur until the groups were anti. It is the same molecule. So beware structures that are drawn in a slightly different conformational arrangement. Well, there you have it. That is it for the E2 reaction mechanism. Elimination bimolecular.